what I want to think about is a fractional factorial situation where I don't collect data from all 8 of those corners, but only from this corner, this one, and that one. Now, as it turns out, that is a good way to choose 4 out of 8 corners. As a preliminary way of understanding that, you might look at that picture and think to yourself, what happens if I collapse this picture, say, left to right? If I take the left face and smash it into the right face and smash it into the left face, if in fact the left face and the right face, there was really not much difference in them, I would have myself a full factorial in factors b and c. That is, this picture says that if I collapse left to right, I'd have a full factorial in b and c. If I collapse top to bottom, I'll have a full factorial in a and c. If I collapse front to back, I get a full factorial in a and b. So a virtue of this thing is that it has a nice is nice and symmetric. So this choice of 4 of 8 corners is nicely symmetric. And it has some other good properties that we'll talk about here as we go along. Let's suppose also that, well, okay, let's suppose that I get data from the 4 circled corners, and I want to think about what could I learn from data from those 4 circled corners. In particular, what about trying to get a handle on the A main effect, having data only from 4 out of 8 of those corners? What I might try to do is to say main effects are base averages minus grand average. I don't have any complete face here, but I might try to take this guy and this guy. Those are the responses on the right face that would correspond to the high level of A. Those are the ones that I have. I don't have anything else. I don't have the 14 and the 12, so I don't imagine that I know those values. But I might take the check mark guys and say average them. So I might take half of check mark plus check mark and then subtract the values for the average of those 2 guys and those 2 guys. So I might subtract a fourth of the corners that I do have. That is, I might try, as a way to get at an A main effect, I'd say to myself that the real main effect is a right face average minus a grand average. I've set this thing up so that this value for the A main effect is 3. So I've set things up so this guy is 3. And now what happens if I take this computation? Well, as if by magic, if I take the 2 corners that I do have on the right face and average their responses and subtract the average of the 4 corners that I do have, what I wind up with is 13 minus 10. I wind up with 3. That looks like magic. What I've done is managed to learn about the A main effect, having only 4 out of 8 corners from that picture. That is, I've computed something that I've called not alpha 2 but alpha 2 star that is, in this case, it turns out to be exactly equal to alpha 2. Looks like I've gotten something for nothing here. I've only paid for 4 out of 8 corners, and I have managed to learn what's the A main effect. Before I get too excited about that, though, let's try that same calculation for not the A main effect, but the C main effect. So I would be talking about coming over here and taking the 2 guys on the back face that I know, the 18 and the 10, and subtracting, taking their average, so that's 18 and 10 average to 14, and then subtract the grand average, and that gets me 14 minus 10 is 4, but, so that's what I've just done here. I've gotten a sort of half fraction version of the C main effect. It's 4, but now that's not so happy because I started with the C main effect being not 4 but 2. That's how I set up this little example. Okay, so I wound up with this guy not being equal to the C main effect. That is, the half fraction version didn't turn out to be the same as the real one, the one that I'm really interested in. That might puzzle me for a while, but what turns out to be the case is this, that the half fraction version of the A main effect is the A main effect plus the BC two-factor interaction. And because when I set this problem up, I set the BC two-factor interaction down here equal to 0, then in my calculation, if this guy is 0, then this fellow and that fellow are the same. But in contrast, I did not set the AB two-factor interaction to 0. That is, the AB two-factor interaction in the way I set the problem up was equal to 2, and so I don't end up having these 2 guys be the same. They're not the same because this guy is 2. The general story here is that these are the things that I can know. So these can be known from a half fraction. And the rest of these, and I can't know this or this individually. All I can know is them plus another term. That's called confounding or aliasing, or I will call it ambiguity, and that comes of necessity with the use of just a fraction of the factorial. Okay, so that's general motivation here. What we're going to do now is to be a little bit more methodical about this and talk about what can we do when we're only going to do a fraction of a 2 to the p factorial. We're going to do that in sort of two pieces. We're going to begin by a careful discussion of what you can do with half fractions. So we're going to be talking about 4 out of 8 combinations for a 2 cubed, 8 out of 16 for a 2 to the 4th, and so on. And then we'll talk about things like, well, what would I do in that Hendrix Kintek example where I have 15 factors, and I'm not going to pay for 32,768 different combinations of 15 factors, but rather I'm only going to pay for 16, for example. The issues that we're going to have to face are these. In the first place, how do I rationally choose the combinations for study? That is, how did I know to choose the 4 out of 8 corners that I chose on that cube? How do I make rational choices of fractional factorials? Once I do that, how did I know this? How did I know this general story here? How did I know what was aliased with what was confounded with what the pattern of ambiguity is? So the second issue is how to determine the aliasing or the confounding pattern. And then finally, how to do data analysis. We're going to do this in 2 chunks. We're first going to talk about half fractions, and then we'll talk about things like quarter fractions, 8th fractions, 16th fractions, and so on. So, 3 issues. Let's talk about the first in the context of half fractions. Here's what we're going to do. We are going to use a prescription that says write out all combinations of, write out a prescription for all combinations of levels of 1 less factor than we have in the study. So we're going to write out combinations for all levels of the first p-1 factors. We're going to write out plus and minus signs for levels of those factors. I'm then going to think about those plus and minus signs as being plus and minus 1s, and we're going to multiply those together to get plus and minus signs, and use those plus and minus, those products, to tell us what to do about the last factor. So here is an example. Let's talk about 4 factors. We're talking about a half fraction, so we're talking about a 2 to the 4 minus 1 fractional factorial. I have factors A, B, C, and D. To follow this prescription, I'm going to look at 3 factors and write out plus and minus signs specifying the 8 different combinations of levels of those 3 factors. I'm then going to multiply those signs together and use them to specify levels of factor D, this last factor. So here's how that proceeds. In this first row, I've got minus, minus, minus. Don't know why some of these things are dropped. I know those things are in the files, but They just didn't copy over to this PDF. What I've got here on the left side of this thing is, in truth table fashion, all 8 combinations of levels of factors A, B, and C. If I multiply together along this first row 3 minus 1s, I'm going to get another minus 1. If I multiply across the second row a plus 1 and 2 minus 1s, I'm going to get a plus 1. If I multiply along the fourth row here, 2 plus signs and a minus sign, 2 plus 1s and a minus 1, I'm going to get a minus 1, and so on. And so the point here is that I've made up a column that is the product of the values in the first 3 columns, and these are what I use to choose levels of factor D. So we're talking about a half fraction of a 2 to the 4th. 4 factors, A, B, C, and D. How do I set levels for D? I use products of signs for A, B, and C. And if I look across this first row, that tells me what? It says one setup of the experiment will be for A low, B low, C low, and then D low. That's a combination that in this special 2 to the P factorial notation we call combination 1. The second row of the table says another way that we will collect data is for A high, B and C low, D high. Well, in this special naming convention for 2 to the P factorials, that is the combination AD, and so on, all the way down to this last row, the ABCD combination. What I've got listed here are 8 out of the 2 to the 4th equals 16 possible A, B, C, D combinations. This is 8 out of 16. This is a good half fraction. Of the 2 to the 4th. This is the one that I get by following my the rules that I just laid down there. As a second example, here's another data set from a chemical study. It's a chemical study that involved, as I say, 5 factors, factor A, B, C, D, and E, each at 2 levels, where the response variable was a color index for some kind of a product made by the process. If I was going to do a full factorial in this context, it would require a minimum of 32 runs of the process. There are 32 ways, that is 2 to the 5th ways, to set this process up, and what we're going to talk about is not a 2 to the 5th, but half of a 2 to the 5th. So we're going to talk about a 2 to the 5 minus 1 so-called fractional factorial. And here are the combinations that Snee actually used in his study. if you count them up, there are a total of 16 out of 32 possible combinations. In this 2 to the 5 minus 1 fraction, fractional factorial. And I'm not going to take time to write it all out now, but you can convince yourself that in fact you get these by following this standard recommendation for choosing the half fraction. By the way, if I come back to this scenario, sorry, wrong one, we'll get there. This scenario, as a matter of fact, the 4 circled corners come from the standard way of choosing a half fraction. That is, if I carefully down here write out A, B, and C, minus, minus, plus, plus, minus, plus, now minus, plus, and I make a product, this would be a plus, this would be a minus, and a plus. If I use that for factor C, this is, and look across this first row, that's combination C, this is combination B, this is combination A, this is combination A, B, C, and the point is that these are the 4 circled corners on that picture. Alright, so let's get back to the discussion here. So that's an answer to how do I do choice of the fraction of the factorial. Second question is, how do I determine the pattern, or the implied pattern of ambiguities if I do things this way? What we're going to do is use a method of so-called formal multiplication, beginning from a quote-unquote generator that describes how we chose the half fraction. And what we did to choose the half fraction was to say that levels of the last factor were gotten as products of the first p minus 1 factors. So we'll start with that as a generator, a quote-unquote generator, and then the rules of multiplication are going to be 2. In the first place, if I take any letter times the letter I get the same letter back again. And if I take the letter times itself, I get I. And that means, for example, in the context of the 2 cubed minus 1, I set levels of factor C using AB products. This thing is the so-called generator here. If I use my methods of formal multiplication, I could take this statement and I could multiply left and right by C, and write C by C is equivalent to ABC. My rules say that any letter times itself is I, and so I have something that says that I is equivalent to ABC. That is a relationship called the defining relationship, and that's going to tell us what is inseparable from what is aliased with what the pattern of ambiguity is. So there is the so-called defining relation, and the first thing that it says is that the grand mean, if you will, mu dot dot dot, and the three-factor interaction are quote-unquote aliased. That is, I cannot put my hands from the half fraction on either of those individually. All I can do is to evaluate their sum. I cannot know either of those things individually. I can't know mu dot dot dot. I can't know alpha beta gamma 222. I can only know their sum. Now if I take this defining relation and I multiply through by A, so if I take I equivalent to A B C, that means A times I is equivalent to A times A B C, and any letter times I is just that letter. Any letter times itself is I times B is B back again, and so I wind up with this relationship. What does that tell me? Well, that tells me that the A main effect and the BC two-factor interaction are indistinguishable. That is, they are confounded, they are aliased. That says, so alpha 2 and beta gamma 222 are quote-unquote aliased. Confounded, I cannot separate those two. As a matter of fact, if you will remember back to what I told you here, that's exactly this statement. I cannot put my hands on the A main effect alone. All I can do is put my hands on the A main effect plus the BC two-factor interaction. That's how I knew to write this relationship down on this slide. Okay, so let's get back to the right one of these things. Get there yet? Okay. And then, so the A main effect is aliased with the BC two-factor interaction. You do the same kind of multiplication. The C main effect is aliased with the AB two-factor interaction, and the whole pattern of ambiguity or confounding or aliasing for this half fraction is that set of four relationships that I've just got written down here for you. That is, I can't tell in the first place the grand mean from the three-factor interaction. I can't tell the A main effect from the BC two-factor interaction. I can't tell the B main effect from the AC interaction, and I cannot tell the C main effect from the AB two-factor interaction. That is, these factorial effects are aliased in four pairs. That makes sense. I can only, if I have data from only four process setups, I can sort of estimate only four things. What are those four things? those four things are, in the first place, grand mean plus 3-factor interaction, A main effect plus BC 2-factor interaction, B main effect plus AC 2-factor interaction, C main effect plus AB 2-factor interaction. So there's the technical meaning. All I can do is put my hands on sums of effects.